Okay, so here is C-11. So suppose a person decides to spend the day sports betting. The amount of money the person has is modeled by a differentiable function f of t, where f of t is measured in dollars and t is measured in hours spent gambling. You are given the graph of f of t below. Evaluate each of the following, interpret your answers in context. And we also have a table of values here, guys. It's just easier to tell the y values from the table than the graph. So, okay, so first we've got f, or actually, okay, modeled by a differentiable function, f of t. So the things we have at play are f prime, and potentially f double prime. So let's just do a little table there and write our units. Okay, so this would be dollars per hour. Dollars per hour. And guys, another way of saying that is hours squared. So that means dollars per hour per hour. Okay, so first we're finding f of 1. Okay, so we are not moving. You move right in the derivative sequence if you are doing a rate of change of something. So if I did a rate of change of f, my units would be moving over 1. If I did the rate of change of f prime, my units would again move over 1 space. Okay, but I'm not taking, this is not a rate of change, this is just a quantity of money. All right, so f of 1, and I'll just look at the table, is $1,200. Okay, so the interpretation, 1 hour into gambling, 1 hour into gambling, the person has $1,200. Okay, now number 2. So f primify. Okay, so guys, f prime, we can use the graph to get it because I have drawn a tangent line, and this is not a perfect tangent. So when we do the slope of this tangent line, which is another way of getting IROC, which is f prime of 5, instantaneous rate of change of f at 5. So it's not a perfect tangent, so this is going to be an approximation, but we could use rise over run on the graph here to get m tan, which would be f prime of 5, because this is the graph of f. Okay, and guys, I noticed that the boxes, the scale is like 1/4 on the x-axis or the t-axis, and the scale is 100 on the y-axis. Okay, so f prime of 5 is approximately, and guys, I'm just going to count rise over run, and I'll go from here to there. So I go up 1, 2, 3, 4. Okay, I just want to show you like how I do it. So 4, and then blank for the scale for each unit, for each box. So I go up 4, and then I go right 1, 2, 3, 4. Okay, so the top, whoops. So the y-axis, each box is 100, and then 0.25 is each box on the x-axis. But actually, this is just 1 there. So 400. Now, so we just did IROC, so we moved over 1. So $400 per hour. Okay, so here's the interpretation. 5 hours into betting or into gambling, the amount of money the person has changes. Okay, how is it changing? F prime is positive, so it's increasing. the amount of money the person has is increasing at an approximate, or I'll say at a rate. I'll say at a rate of approximately $400 per hour. Okay, there's that. And now number 3, this is A-Rock. So A-Rock on 4 to 8. All right, so this is number 3. So A-Rock on 4 to 8. Okay, now guys, the thing about A-Rock is that you don't actually take the derivative, but you are getting a rate of change. So the units are still going to move over 1. So our units are going to be dollars per hour, but we are not actually like taking a derivative. So we're not finding the slope of the tangent line, we're finding the slope of the secant line. So A-Rock on 4 to 8 is f of 8 minus f of 4 over 8 minus 4. Okay, so f of 8, I'm just going to use the table. So f of 8, 18, 13, minus 8 minus 4 is 4. Okay, so let me get this in the calculator. Okay, so this is $161.998 per hour. Okay, so darn, I'm running out of room. Okay, so I have to do the interpretation, so I'll do it up here. So number 3, all right, this is number 3 continued. Okay, from 4 to 8 hours into bedding, the amount of money the person has is increasing at an average rate of 160 I guess 162. I guess we could, I don't know, I'll just do 998 per hour. Okay, so from 4 to 8 hours into bedding, the amount of money the person has is increasing at an average rate of $162 per hour. Okay, notice guys, for A-Rock, you have to say average rate. For I-Rock, you don't have to say instantaneous rate. If you say rate, it is implied that it is at an instant. Okay, so there's that. Now guys, so the topic here is particle motion. That actually had nothing to do with particle motion, but the next example will. And guys, this is looking to be kind of a long video, so please take a break if you're losing focus. And one way of gaining focus is to maybe try to get ahead of me. So, all right, this is page 31. So now we begin particle motion. We need to know the information in the table below. So, position. All right, this is the position of a particle. Here's its velocity, here's its acceleration. The velocity is the rate of change, is the I-Rock of the position. The instantaneous rate of change in position. So that's velocity. And then the rate of change of the rate of change is acceleration. Okay, so velocity itself could be increasing or decreasing. And okay, so here's the information, guys, that we need to know. A particle will be at rest, meaning it's just staying at its position, if velocity is 0, and vice versa. A particle will be moving right or up. We're usually in AP Calculus, AB going to be moving on a horizontal or vertical line. So we'll be moving right or up if velocity is positive, down or left if velocity is negative. We will be changing direction from moving right to left or up and down, vice versa. Changes direction if velocity has a sign change. So it changes from a positive to negative value. A particle will be speeding up if both velocity and acceleration are positive or if they are both negative. So basically, if velocity and acceleration have the same sign, then the particle is speeding up. Its speed is increasing. Its speed would be decreasing, another way of saying slowing down, if the velocity and acceleration have opposite signs, so they are not agreeing. Okay, so let's do this problem. So suppose we are observing a squirrel run back and forth on a wire that is modeled by the x-axis. Its position on the wire is modeled by S of t, which is equal to this, where S of t is measured in meters and t is measured in seconds. Okay, and then we're going to do like all of this stuff. So whenever you're dealing with particle motion, and by the way, they didn't say that this was differentiable, but we know that it is. It's actually twice differentiable. We can actually just keep taking the derivative. This is a polynomial. So we've got a derivative sequence. So we've got S, S prime, S double prime. Okay, and in a particle motion context, the first derivative is velocity and the second derivative is acceleration. Okay, so V and S prime are the same thing, and then same thing there. Okay, so let's put our units in. So meters, and then meters per seconds. Meters per second, which is in notation, you could do meters per second squared. Okay, so the average velocity, so A. Okay, now guys, here's the thing. Average velocity, so we're gonna be doing a rate of change. So it's like our units are gonna be moving right, but we are not taking the derivative, okay? Average velocity is not the derivative. You could use it to sometimes estimate the derivative, but it is not the derivative. So average velocity, so we're going to do AROC. In the first 3 seconds will be from 0 to 3. So AROC on 0 to 3 is S of 3 minus S of 0 over 3 minus 0. Okay, so I'm just plugging into the original. So I am not taking the derivative. Ah, shoot. All right, I messed up. Okay, so 27 plus 6 times 9 minus 15 times 3. Okay, so 36 minus 0 over 3. 12. Okay, now we didn't take the derivative, like S prime is not involved in any way here, but this is an average rate of change, so meters per second is the units. Okay, that's the average velocity. Okay, so yeah, and maybe for your notes, guys, so average velocity, that would be AROC. Okay, part B, find the instantaneous velocity. Instantaneous is optional to say. Okay, it's implied. Find the instantaneous velocity of the squirrel at 3 seconds. So here we do need to take the derivative. So this is I rock. So this we need to do S prime of t. 3t squared plus 12t minus 15, okay? So this is the velocity. So you could leave it S prime or you could say v of t, and you never even needed to use S prime really. All right, so that's, oh shoot. I need v of 3. All right, so you take the derivative, that's the velocity function, and then you plug 3 in. So 27 plus 36 minus 15. 48 meters per second. Okay. All right, C. Find the position, velocity, and acceleration of the squirrel at t equals 4. Okay, so the position, so this is part C. So the position is S of 4. So I just take 4 and I plug it in here. So 4 cubed plus 6 times 16 minus 15 times 4. Okay, is 100 meters. Okay, so we've got a wire, and you know there's some point on the wire that corresponds to the origin, and we're 100 meters to the right of that point. And okay, so that's the position. Now the velocity comes from this function. You would plug 4 into this function. So that's 3 times 16 plus 48 minus 15. Okay, 81 meters per second. Okay, and then now we also need the acceleration. Now to do acceleration, you need to do the second derivative of s, which would be the first derivative of s prime, which is the derivative of velocity. So I just take my velocity function, which is here, and for acceleration, I get 6t plus 12. So a of 4 equals 24 plus 12, 36 meters per second. Okay. All right, now for part C. So now parts D and E, we're going to explain things about our part C solutions. So D, at t equals 4, is the squirrel traveling left or right, or is it at rest? Explain. Okay, so D. So this is where we've got to be thinking of this. So is the squirrel moving left or right? So that information is going to be here. Okay, so when velocity is positive, the squirrel will be moving right. If it's negative, the squirrel will be moving left. So since velocity at 4 is positive, okay, so v of 4 equals 81, which is greater than 0. Okay, so we can say traveling left or right? Moving right, because v of 4 is greater than 0. Okay, so that's D. Now E. At t equals 4, is the squirrel speeding up or slowing down? Explain. Okay, guys, a lot of times people think, oh, it would be speeding up if acceleration were positive. It would be slowing down if acceleration were negative. No. The sign of acceleration tells you nothing without looking at it, or without looking at the sign on velocity as well. So the squirrel will be speeding up if the acceleration sign agrees with the velocity sign. It's like it's pushing it in the same direction, but it will be slowing down if their signs do not agree. So for E, so V of 4 is 81 is greater than 0. Acceleration of 4 is 36 is also greater than 0. Okay, so the answer is speeding up since B of 4 and A of 4, excuse me, are both greater than 0. Okay, or you could say because V of 4 and A of 4 are both positive, or because V of 4 and A of 4 have the same sign. That would work as well. Okay, find all times at which the squirrel is at rest. Okay, so all times at which the squirrel is at rest. So you need to know that if you're looking for where a particle is at rest, that is where the velocity is 0. Okay, so what you need to do anytime you're asked this question is take the derivative and set it equal to 0. And we actually already do have the derivative. Okay, so let me just rewrite it. 3t squared plus 12t plus 15. Okay, so you're going to set it equal to 0, so we're going to have to factor. Okay, so 3t plus 5. Okay, so t equals negative 5. T equals 1. Okay, so it's just going to be 1 because we can't have negative time. So at rest, squirrel at rest at t equals 1 second. Okay, and now find the position of the squirrel at those times. So E, F, G. So how are you going to get the position? That's S. So you're going to plug in. So S of 1 is equal to 1 plus 6 minus 15. Negative 8 meters. Okay, so there is this, we're on a wire. There is some point on the wire that was selected to correspond to the origin, and we are 8 meters to the left of that point. Okay, so there's that, guys. Sorry about the long video, but I will talk to you soon.